Hi guys, I'm sorry that I'm not there. I feel really bad about it. And I don't want you to keep like just sitting in a classroom doing whatever. So I want to get you started on moving along to bigger and better things in calculus. And we will of course go over all of this stuff when I return on Monday. And I fully expect to return healthy and ready to go. So we're going to go into chapter 4 today. In your book, that's page 193, okay? And we're going to find the derivative of a function. And so far, you know that the derivative of a function is equal to the limit as the width of the interval approaches 0 of the difference quotient, right? We don't like that formula. It's a pain, it's tedious, we can make mistakes, and we want something fast and efficient. So we're going to learn some fast and efficient rules, okay? So the first rule is derivative of linear functions. So these are functions of the form y equals to mx plus b. And guess what? The derivative of y equals to mx plus b is just the slope of the line itself. So for example, if f of x equals 2x plus 5, then the derivative of this function is 2. End of the story. Now I'm going to show you why that is in a few minutes, but for right now, just memorize the rule. So anytime you see a linear function, not a constant function, that's different, we're going to talk about that in a second, but a linear function, so of this form, the derivative is just the slope. I don't know, here's another example. Y is equal to 1/2 x minus 2. What's the derivative of this function? It's 1/2. Okay, it's just the slope of the line. So just memorize that and you'll be good. And you know, the reason why, so look, let's just say over here, we have y is equal to 2x plus 2. So that line has a y-intercept of 0, 2, and it has a slope of 2, so that looks like a 2 to me. Here's my line, right? The idea is this, is that if I draw a tangent line anywhere along this line, the slopes are the same because the lines are parallel. They're actually coincident lines. One's right on top of the other. So that's the reason why the derivative of a linear function is the slope itself. Hi Ella. Sorry, my dog's being a PETA tonight. Huh, yes it is. Okay, alright. Okay, lay down for a little bit, okay? Alright, so now that brings us to the constant function. Constant functions are flat lines, right? So for instance, y is equal to 2. You would go up 2 on, this is when x is 0, right? Remember, our lines are in the form mx plus b. So this would be 0x plus 2, right? 0 times x is 0, so y is equal to 2. So these are lines that are flat. So guess what? If we draw a tangent line anywhere on this line, the slope of that tangent line is going to be 0. So the derivative of a constant function is always 0, okay? So the derivative of a constant function, or a constant, just a derivative of a constant even, is equal to 0, okay? So if I said to you, f of x equals 10, find f prime of x, you would say f prime of x is 0. Okay, it's as simple as that. Just memorize it. Okay, the next rule is super important. It's called the power rule, and you're going to use it a lot. It's not the most powerful rule, but it's a pretty powerful rule. And we're going to use the power rule when we have a variable raised to an exponent. So let's suppose we have a function that equals x to the n, okay? X is my variable and n is some number. Maybe it's a cube, maybe it's a fourth, who knows, okay? the derivative of this thing goes as follows. You take this exponent, whatever the number is, and you bring it down and multiply it to the coefficient of x. So right now the coefficient of x here is 1. So it's n times x to the n minus 1. The idea is you multiply it to the coefficient of the variable, and then you subtract 1 from the power. A simple example would be, f of x is equal to x squared. Well, by this rule, the derivative of x squared would be 2 times x to the 2 minus 1 is 1, so we just leave that alone. Okay? Let's see. F of x is equal to, t to the 5th. Then the derivative of that thing would be 5 times t to the 5 minus 1 is 4. Capiche? Okay. Now, if I have a polynomial, so I'm not going, this is in the book, but I'm not going, step by step. I actually have the book right here, and I just want to make sure I don't miss anything from this section, because I'm going to have you do some practice from this section. What was I going to say? But a lot of times, you're not just going to have simple functions like that. You're going to have something like, 6x squared minus 10x plus 12 or something. And you're going to be asked, hey, what's the derivative of that function? Well, the idea is you can just take the derivative piece by piece. So if I want to apply the power rule to this piece, I would have 2 times 6, x to the 2 minus 1 is 1. Here, I have a 1 here, right? There's a 1 on this x. So if I bring the 1 down, it's negative 10 times x to the 1 minus 1. I'm going to write that one there just for a point. And then this is a constant, and the derivative of a constant is 0. So when all is said and done, I'm going to have 12x minus, now look, this becomes 10x to the 0, and I'm not going to tack the 0 on there. And what's x to the 0? It's 1. So it would be 12x minus 10. Okay, I just did that using a combination of the power rule and or this constant multiple rule, which I'll discuss in a second. Okay, so here's another one. F of x is equal to 4x cubed minus 3x squared minus 2x plus 5. The derivative, piece by piece, would be 12x squared minus 6x minus 2. Okay, so whenever I have x to the first power, I really don't think about it. I know the x sort of goes poof, it goes away, and I'm done. All right. Now, another thing you're going to see in this section, but don't get too hung up on it, is Leibniz notation. So, for example, I'm going to use the same function again. F of x is 4x cubed minus 3x squared. I'm going to cut off the other half, so I'm just going to use part of that function to show you something. There's something called a constant multiple rule. And what that means is that you can pull the constant out for a second to get it out of your way. Focus on the derivative, because derivatives are always taken with respect to a variable, and for right now it's just going to be the variable x. So, you're not really taking derivatives of numbers unless it's a constant and you know that it's 0. So anything else with a variable, you're pretty much going to use the power rule for right now. So this may not seem like a big deal right now, but if those exponents become fractional, it's going to become a big deal really fast. So I could say the derivative of this thing is equal to 4 times the derivative with respect to x of x cubed minus 3 times the derivative with respect to x of x squared. Now what am I doing? These two notations here, that's that Leibniz notation, okay? It says the derivative with respect to the variable x. So I'm pulling this 4, which is a constant multiple, over to the side for a second, and I'm focusing on, hey, what's the derivative of x cubed? Well, using the power rule, I know the derivative of x cubed is 3x squared, right? And then I'm pulling this 3 out, and then I'm going to take or focus on the derivative of x squared. Well, I know that that's 2x, and then I multiply it back in. So if you look at the first two terms of our derivative function, anyway, they match exactly. So that's the constant multiple rule, and you may see this ddx, and it means the same thing as f prime of x. What's the derivative of the function? Okay. What else is in here? Yeah, fractional exponent. So for example, suppose I say g of x is equal to x to the 3/2 minus x to the 1/2 minus x to the -1/2. I know that looks ugly, but guess what? You're going to do the same thing. This is a variable, it's raised to a numerical exponent, so I'm going to use the power rule piece by piece, all right? So I would tell the grader g prime of x is equal to 3/2 times x to the 3/2 minus 1 minus 1/2 x to the 1/2 minus 1 minus a -1/2 x to the -1/2 minus 1. Now after today, or maybe by the next cycle, you're not going to have to write this down. You're going to do them in your head, but I'm doing this to show a point. You know, it's easy to bring a fractional exponent down front, multiply it to 1 or to any other number actually. This is where it gets a little bit like, ooh, I got to deal with fractions. So it's just 2 times a -1 is -2, plus 3 is a positive 1/2, right? Minus 1/2 times x to the 1/2 minus 1 is a -1/2. A negative makes that a positive 1/2. X to the -1/2 minus 1 is -3/2. Now we don't make, you know, negative exponents positive in calculus. We leave them just like that. So if you're asked for the derivative of something like this, just take it piece by piece and be careful with your fractions, and write it out. And by the way, here's a little trick. So you see up here where I have 3/2 minus 1. The answer, when we clean that up, is 1/2, right? So you just do 3 top minus bottom. So 3 minus 2 is 1, back over the bottom. Same thing here. 1 minus 2 is -1 over the bottom. Make sense? I don't know, p of x equals to x to the 7/8, right? So some weird little fraction. So p prime of x will be 7/8 x to the 7/8 minus 1. I can do it that way, or I can remember that little trick. I can say, well, by the way, this is -8 plus 7 will give me a -1/8 that I should get. So I do 7 top minus bottom. 7 minus 8 is -1. That goes on top over the bottom. Same answer. Pretty cool, eh? So what you're going to do today is you're going to practice these techniques, and you're going to go to page 200, and you're going to do 1 through 17 odd. Now if you get stuck on something, I need you to notify me on ESB. That way I can go over any homework questions in the next video. So, you know, I'd be uploading the next video tomorrow night, or no, Thursday night. So I need them by Thursday night if you get stuck. So you should do these in class. You should watch this video in class, do the practice in class, and that way if you get stuck on anything, or you're not sure, or your answer doesn't match what Bob has, then you can say, hey, can you go over, you know, number 3 in the next video, and I will do it. Okay? So anyway, that's the lesson for today. I hope it works out, because my videotaping is terrible, and I will see you again via video on Friday. Have a good day.